Good morning. Today we are going to discussing about Newton's rings. So when a plano convex lens of large radius of curvature is placed with its curved surface on a plain glass plate, a thin film of air is enclosed between the lower surface of lens and the upper surface of the glass plate. That is, this is the plano convex lens. A convex lens means one side is bulged like this, and plano means one side is plano. So plano convex lens. So this is the plano convex lens which is placed on the surface of a glass plate. Okay. So this is the setup. So when the plano convex lens is placed on a glass plate, an air film is formed between the plano convex lens and glass plate. From this point of contact, this is the point of contact between the lens and the glass plate. From this point to this point, an air film is formed between this region. Okay. The thickness of the air film at the point of contact is 0, and the thickness of the air film increases towards from the point of contact. So here the thickness of the air film is 0, and the thickness of air film is going to increase from this point to this. That is, the thickness is increasing as we going from this point to this point. Okay. When a monochromatic light from an extended source is made to incident normally on the film, and the film is seen reflected light through a microscope, we get a dark spot at the center, surrounded by alternate concentric bright and dark fringes. That is, what we are doing is we are placing a monochromatic source. A monochromatic source of light here, and this is allowed to fall on this glass plate normally. So what will happen is this light will fall on this plano convex lens, so which may transmit to this region and get reflected back. Okay, so this if we are observing the reflected light through a microscope placed here, we can see a dark spot at the center, and which will be surrounded by alternate dark and bright fringes. Okay, so the fringes will be in the form of ring. This is because the central point is dark. Okay, and this is curved in shape. That is, this is a plano convex lens and this is circular in shape, and the air film thickness on the if you are viewing from the upper side, this lens is circular in shape, and so the thickness of the air film between the lens and the glass plate is varying, is increasing in circular. That is, for this point, this is the thickness is 0, and consider this point. This point, the thickness is say T, and correspondingly at the same distance from this point O here, the thickness will be T, and this will be if you are viewing from the upper side, this will be like a circle. That is, with this, if this is a distance of R, and similarly to this left side R, then this will represent a circle. Okay, so in this circle of radius R, the thickness will be T. And if you are considering another point here, say here, the thickness say T1, and at the same distance here the thickness will be T1. And if you are viewing from the upper side, then along this circle, say if it is at a distance R2, then along this R2 this will be thickness will be T2. So since the plano-convex lens is in circular in shape, the thickness of the air film is varying along the radius of this circular shape, so that the bright and dark fringes will be circular in shape. So we will get a bright dark spot. Dark spot occurs because here at the point of contact the air film is 0, so no path difference between the reflected ray is taking place. So the path difference is 0, so a bright dark spot at the center. And as the thickness of the air film varies from this point, we will get alternate bright and dark fringes according to the condition which satisfies the condition for bright or dark fringes. Okay, so this is how we are obtaining Newton's rings in the Newton's ring arrangement. This was first observed by Newton, and so it is known as Newton's rings. Okay, so Newton's rings are formed due to interference between the light waves reflected from the lower surface of the lens and the upper surface of the glass plate. The air film is symmetrical around the point of contact. All the points of a given thickness are equidistant from the center and they lie on a circle. If a point appears dark, all the points along the circle are dark. Since the thickness of the air film is same, if dark rings is produced, so the dark ring is produced if the points appear bright, we get a bright ring. Thus alternate bright and dark rings of radii are observed. These rings are concentric in nature, that I have explained just before, and the fringes are obtained due to the interference of the light reflected from the bottom surface. Bottom surface means the light can be reflected from the upper surface of the plano-convex lens or from the lower surface. So the light reflected from the lower surface of the plano-convex lens and the top surface of the glass plate. So the interference of this light will produce the rings, Newton's rings, and which will be circular in shape as I have explained before. And according to the condition of bright or dark fringes or constructive or destructive interference, we will get bright or dark fringes on the screen. Okay, and this will be concentric circles. This is because of the circular nature of the varying film thickness, that is air film thickness. This happens because of the circular shape of this plano-convex lens. Okay. The thickness of the air film at the center is 0 due to the reflection from the glass plate. Only path difference of lambda by 2 is produced for the reflected rays, and this is a condition for darkness. So the center of Newton's rings pattern is dark. So since the film thickness is 0, the reflection from the glass plate. Reflection from the glass plate means when the light falling on this central point, the reflection is taking from this point. So this can produce only a path difference of lambda by 2, which we have seen in the last class, that a thin film can reflection from a film can cause a lambda by 2 path difference for the reflected rays, and this is the condition for darkness. So this leads to a dark fringes at the central point. Okay, now we can look at the theory of Newton's rings and the reflected light, what happens. So Here we have shown a picture. This is plano convex lens and this is the glass plate, and the point of contact is marked as O. And we are marking, suppose R is the radius of curvature of this plano convex lens. So we are marking the center of this circle as C, and we are considering a point or an air film of thickness T. We have marked this thickness as T, which is BD, thickness T, at a distance Rn from the point of contact O. Okay, and we have marked this. This is nothing but the radius of curvature of the plano convex lens. So this is marked as capital R. Okay, and this point, from this point C to O, this is again R. Okay, but this point EO or OE is nothing but T itself, that is the thickness. Because from this figure it is clear this is the air film thickness. Since this is T, this OE is also T. So the total distance OC is nothing but, sorry, CE is nothing but OC minus OE. Okay, which is R minus T. So this is the incident ray. So we have shown in this picture the incident ray, and a part of this is reflected from the lower part, and from the another part is reflected from the glass plate, and this reflected rays are interfere, and due to the varying thickness of this air film we will get alternate dark and bright fringes. So we have seen this picture. So in order to find the radius of the nth dark ring, so at this point we will get dark spot and surrounding this alternate bright and dark fringes, which is concentric in nature. Let the dark ring of radius Rn is formed through B. So we are considering a dark ring at a point B, which is of air film thickness T, which is at a distance Rn from the central dark point. Okay, so from this figure, CB square is triangle, from triangle CBE, CB square is BE square plus CE square. CB is nothing but R, so R square is equal to, we have taken this as Rn square plus R minus T all square. Okay, so from this we will get, if we are solving this, expanding this according to A minus B all square and cancelling the same terms on both sides, and we will obtain Rn square is equal to 2RT. In this for getting this equation here, neglecting the T square term, because T is the air film thickness which is very small, so we will neglect the T square term. Then we will end up with Rn square is equal to 2RT. The condition for the formation of dark ring is 2 mu T cos R is equal to N lambda, which we have seen in the previous topic, that is thin film interference. 2 mu T cos R is equal to N lambda is the condition for dark ring. Since the light is incident normally, we will get R is equal to 0, that is angle of refraction is 0, and for air film mu is equal to 1. Since the film this region is filled with air, the mu is refractive index is 1. So we can get 2t is equal to n lambda. Substituting in equation 2, that is, we are obtaining this equation by substituting in equation 2. This equation is substituting in this equation. So we will get Rn square is equal to nr lambda. That is, t, from this t is equal to n lambda by 2. Here substituting this here, we will get Rn square is equal to nr lambda, or Rn is equal to square root of nr lambda. So the radius of nth is nothing but nr into lambda. Here Rn is nothing but the distance from the central point to this dark ring at a distance Rn, where Rn can, so this is circular in nature, so this Rn is actually the radius of the dark ring. Okay. So this is the expression for radius of the dark ring, square root of nr into lambda. For a given wavelength lambda and radius of curvature r, this is the expression. So Rn is proportional to square root of n. That is, radius of nth dark ring is proportional to square root of the natural numbers. As n increases, the distance between the rings decreases. That is, the rings come closer as we move away from the center. That is, Rn is increasing as n is increasing. N is increasing means the natural number increases. That is, as we are counting the rings 1, 2, 3, etc., the Rn is increasing as we are counting more and more rings, and also the separation between the rings is decreasing. So the rings will be more and more closer when we are counting to higher and higher numbers of the rings. Now we can find the radius of the bright ring. Radius of the bright rings similarly can be obtained by applying the condition for bright ring. So if you are applying the condition for bright ring, this is the condition. Again we can take mu is equal to 1 and r is equal to 0, so that 2t is equal to 2n plus 1 lambda by 2. From this, the radius of the bright fringe we will obtain 2n plus 1 lambda r by 2, where n varying from 0, 1, 2, etc. So this is the radius of the bright ring. Now we have to find out the wavelengths. We can find out the wavelength of a given source of light using Newton's ring arrangement. For this, we will do in our lab for your practicals. So you can do this in lab. For this, you are given with a source of light and a Newton's rings apparatus. Newton's rings apparatus includes a plano-convex lens and a glass plate. So what we are doing is, you are allowed to fold this source. This is a source of light, so we are allowed to fold this source light normally on this arrangements. That is the plano-convex lens placed on the glass plate. So if you are placing this source of light here and allowed to fall on a glass plate at a 45 degree, which will be make a setup in which the light will fall normally on this arrangement. So this is how we are arranging to get normal incidence on this surface. A microscope is placed here so that you can observe the interference pattern through this microscope, where the reflected light from the bottom surface of the plano convex lens and upper surface of the glass plate will interfere, and you can see this interference fringes through this microscope. So this is the arrangement, and how you will get or calculate the wavelength of the given source. So we know the radius of the nth dark ring is square root of nr lambda by nr lambda. So if we are squaring on both sides, we will get rn square is equal to nr lambda. Here rn or r is the radius, so the radius can be written in terms of diameter as diameter by 2, or if you are representing diameter by capital D, which is d by 2. So r is capital D by 2. So if you are writing the r square in terms of d, we will get d by 2 all square on the left side, and the right side nr lambda. So this d by 2, from the d by 2 all square, that d square is keeping on left and this 2 square is taking to the right side, so we will get 4 nr lambda. So this is equation 1. So dn is the diameter of the nth dark ring. If you are considering n plus kth ring, we will obtain similarly as dn plus k square as 4 n plus k instead of a n plus k r lambda. So we will get two equations like this. If you are subtracting equation 1 minus 2, we will get 4k r lambda. If you are 4k on the right side, on the left side now, 4k r lambda is equal to dn plus k square minus dn square, from which we will get lambda as dn plus k square minus dn square, or 4k r. So with the help of a traveling microscope, the diameter of nth and n plus kth dark ring can be measured. So what we are doing in experiment is that we are observing from the experimental setup is like this, and we are observing this from the upper side, and we can move this traveling microscope on this side and this side, and we can see the fringe pattern on this side and this side of the central dark point. So we can place the crosswire of this microscope on the particular fringe, and so that we can locate the nth ring or n plus kth ring, etc. Okay, so that we can locate or measure diameter of the rings. So from knowing the value of r, that is the radius of curvature of the plano convex lens, which we can measure separately, lambda can be calculated, because k is a number and r is the radius of curvature, and we can measure the diameters from using the microscope. So knowing all these values, we can measure the wavelength of the given light. So this is how we are measuring the wavelength of a given source of light using Newton's ring apparatus arrangement. Okay, so this is about Newton's rings. Okay, thank you.